Stability and determinacy in truss structures. A truss is geometrically stable if it can maintain its position and configuration under applied loads, even though such a structure deforms when loads are placed on it. But once the loads are removed, it would assume its original, undeformed configuration. In contrast, deformations or displacements in an unstable truss are permanent and often occur without any significant applied loads. So, this is a stable truss, and this is not. We say that for a stable structure, the equilibrium conditions are always satisfied, regardless of the position or direction of the applied loads. So, to prove that a truss is stable, we need to show that the equilibrium equations hold true under all possible loading cases. Conversely, if we can find even a single loading case for which the equilibrium equations cannot be satisfied, then we must conclude that the truss is unstable. For example, consider this simple truss. If we apply a vertical load at C, it can be argued that since the conditions of equilibrium are met, the truss must be stable. But this is not a valid argument, since there is another load case for which an equilibrium condition does not hold. If we apply a non-zero load in the horizontal direction at C, we get the following equations. Note that sum of the forces in the x direction is not zero. It equals P. So this relationship does not hold true. Therefore, we label the truss as unstable. We may also be able to determine this kind of instability by visual inspection and a bit of intuitive reasoning. The line of reasoning could go like this. The truss rests on 3 rollers, but there is nothing to prevent the entire truss from rolling along the horizontal plane. Since this type of rigid body motion is not permissible in stable static structures, the truss must be unstable. Now let's examine a less obvious case. Consider this truss. The structure is secured against rolling using 2 pin connections. Is the truss stable? Or, put it differently, can we prove its instability? To answer this question, let's examine the equilibrium equations associated with the structure. Suppose we apply a non-zero force at P at joint B. What does the system of equilibrium equations tell us? Here is the free body diagram of the entire system, and here are the equilibrium equations. The system seems to be solvable, right? The third equation gives dy equals P. Then from the second equation, we can determine ay. Ay equals negative P. And although we cannot solve for ax and dx using the first equation, the equality holds. That is, we can easily find values for ax and dx that add up to negative P. So, are we to conclude that this truss is stable? Not quite. We just showed that the truss is externally stable. That is, we showed that the supports could keep the structure in static equilibrium. But that does not say anything about the stability of the truss itself, which depends entirely on the number and orientation of truss members and their interconnectivity. We refer to the stability of the truss configuration as internal stability. An externally stable structure is not necessarily stable internally. So how do we answer the internal stability question for trusses? A convenient way to determine internal instability is to locate a part of the truss that violates one or more of the equilibrium equations. For example, we know that the free body diagram of a stable rigid body must contain more than one non-zero force in a given direction, say, in the x direction. Otherwise, the corresponding equilibrium equation cannot be satisfied. So, let's see if we can find a substructure in this truss whose free body diagram has only one non-zero force in the x direction. Does such a substructure exist? Yes, it does. I can divide the truss into two substructures by cutting through the two vertical members. The free body diagram of the top part looks like this. The diagram shows three forces, two unknown forces in the y direction and one non-zero force in the x direction. For this rigid body to be in equilibrium, all three equilibrium equations must hold true. But this equation does not hold true as p is different than 0. Therefore, we can conclude that the entire truss is unstable. What about this truss? How can we show it is unstable? We know the truss is externally stable as there are enough support reactions to prevent rigid body motion of the entire structure. So its instability must be internal. But how to prove it? Is there a substructure here whose equilibrium cannot be maintained? Yes. Similar to the previous example, I see three vertical members separating two parts of the truss. If I cut through these members, only vertical member forces appear on the free body diagram. But then if we apply a horizontal load to the top left joint of the truss, the free body diagram becomes this, which results in this equation. The equation violates the equilibrium conditions. It shows that sum of the forces in the x direction is not 0. So, the truss must be unstable. Sometimes, we may be able to determine if a truss is unstable by counting and comparing the number of equilibrium equations with the number of unknowns. Recalling the method of joints, the number of joint equilibrium equations in a truss equals 2 times the number of joints. And the number of unknowns equals the number of support reactions plus the number of member forces. If the number of equations is greater than the number of unknowns, the truss is unstable. So here we have 8 equations, but only 7 unknowns. So the truss must be unstable. Let's see how this counting rule works for the other trusses we have examined so far. Truss 1. Number of equations is 4 times 2, or 8. Number of unknowns is 5 plus 3, or 8. 8 equals 8. So the rule did not work here. It could not correctly identify the truss as unstable. Truss 2. Number of equations is 4 times 2, or 8. Number of unknowns is 4 plus 4, or 8. 8 equals 8. The counting method does not work for this truss either. How about this truss? Number of equations, 2 times 6, or 12. Number of unknowns, 9 plus 3, or 12. Again, the method fails to identify the truss as unstable. With deciding on the stability of a truss, it may be necessary to go beyond just counting the number of equations and unknowns. We may have to actually examine the equilibrium equations to identify a source of instability in the truss. Consider this structure. Is it unstable? Is there a substructure whose free body diagram violates one of the equilibrium equations? I cannot locate such a substructure, but still have a hunch that the truss might be unstable. What to do now? How about actually writing out and trying to solve the joint equilibrium equations? Yes, might be a lot of work, but I'll then know for sure if the truss is unstable. Here are the joint equilibrium equations. For joint B, we can write, for C, we write, for D, we have, this equation tells us FAD is 0. Then from this equation, we can conclude FCD is also 0. And for joint A, we get Are the equations consistent? We can definitely answer the question by going through the process of solving the equations for the unknowns, say, using the Gaussian elimination method. But in this case, we don't have to. When I visually scan the equations, I notice a problem. The equation says FAB equals 0. But this one says FAB equals P. And since P is not 0, then we have contradictory equations. This implies the truss is unstable. How about this truss? Is it unstable? First, let's see if the counting technique gives us the answer. There are 14 equations and 14 unknowns. So, no, this does not allow us to conclude that the truss is unstable. Now let's try to find an unstable substructure in the truss. Does such a substructure exist? Yes, I found one. Here is a clue. Say there is a vertical load here. We can draw the free body diagram of the entire system like this. At this point, it should be clear that neither AY nor BY can be 0, else the truss becomes externally unstable. With that in mind, can you find an unstable substructure here? Pause the video if you want to give it a try. What if we cut the truss like this and drew the free body diagram for the right segment? If we write the moment equilibrium equation, say, about point C, we get this equation is satisfiable only if By is 0. But we already have concluded that By cannot be 0. So, this relationship does not hold true. Therefore, we have an unstable truss. Here is another truss, which is somewhat similar to the previous one. Can we show it is unstable? Pause the video and give it a try. No matter how hard you try, you cannot prove that this truss is unstable. Why? Because it is stable. Here is the proof. First, let's introduce a couple of facts. Fact 1. This truss configuration is stable. Why? Because the two pin connections make it externally stable. And the A-shaped configuration of the two truss members ensure that the force equilibrium equations for joint A are satisfied regardless of the direction of the applied load. Fact 2. Given a stable truss, if we add two non-collinear members to it, the new truss, having one additional joint and two additional members, is also stable. So if we add these members to this stable truss, we get this stable truss. Again, if we add these elements to this stable truss, we get this stable truss. Hopefully you see where I'm going with this. We can continue adding pairs of non-collinear members to the truss until we arrive at our target geometry. Therefore, this truss configuration is stable. When trying to determine the stability of such a truss, it may be more helpful to take away non-collinear members instead of adding them. Let me explain what I mean by that. Here is a truss. Say, I cannot immediately see any unstable substructure, but I see a joint that connects two non-collinear members. So I'm going to reason that if indeed the entire truss is stable, then what remains after removing these two members must also be stable. Notice that here I am using fact 2, which I mentioned a minute ago. That is, a stable truss plus this pair of elements equals a stable truss. Conversely, a stable truss minus this pair of elements is also a stable truss. Let's continue this reduction process. If this is stable, then this configuration must also be stable. This configuration must also be stable. And so should this one. By reducing the truss this way, we eventually arrive at a configuration that might make it easier to deduce the system's instability. Here, we arrive at this simple stable configuration. Here are a few exercise problems. A stable truss is either statically determinate or indeterminate. If the number of joint equilibrium equations equals to the number of unknown forces in a stable truss, we call it statically determinate. On the other hand, if the number of unknowns is greater than the number of equations, the truss is said to be statically indeterminate. Here are a few stable trusses. This one is statically determinate as the number of equilibrium equations equals to the number of unknown forces. This truss has 8 equilibrium equations and 9 unknowns, so it is indeterminate. We refer to the difference between the two numbers as the degree of indeterminacy of the truss. So in this case, the degree of indeterminacy is 1. This means if we remove one of the unknown forces, the truss becomes statically determinate. This truss is statically indeterminate, and its degree of indeterminacy is 2. Sometimes it may be useful to indicate if a truss is indeterminate externally or internally. If there are too many unknown support reactions, we call the truss externally indeterminate. If there are too many truss members, we call the truss internally indeterminate. What do I mean by too many support reactions or truss members? If we cannot determine all the support reactions using the 3 rigid body equilibrium equations, then the truss is said to be externally indeterminate. If the indeterminacy is not due to redundant support reactions, then it must be due to the presence of extra truss members. We refer to such a truss as internally indeterminate. Here is an externally indeterminate truss. Its degree of indeterminacy is 1. This truss is internally indeterminate. It has a degree of indeterminacy of 2, and this one is indeterminate both internally and externally. Total degree of indeterminacy is 3. The truss is externally indeterminate to the first degree and internally indeterminate to the second degree. What is the degree of indeterminacy of this truss? The truss is indeterminate to the first degree. In spite of having 4 support reactions, this truss is not indeterminate externally. Why? Because we can determine all the support reactions by writing and solving 2 sets of equilibrium equations, one set for the left substructure and one set for the right substructure. The indeterminacy here is internal, due to the presence of an extra, redundant, member in the right substructure. See if you can correctly label the following trusses as externally or internally indeterminate.